going to be speaking today about one aspect of that new perspective, the modelling guide JCGEM 103, which is being developed right now and we hope will be published later this year or at the latest next year. I'm going to be talking about modelling the measurement principle and then choosing a form for the model, and then the necessity of extending the model to take account of meteorological influences, and then give some examples and give some take-home messages. First of all, some background. We need a measurement model when we're going to propagate uncertainty, and that the measurement model depends on the nature of the measurement. And that means that developing a measurement model might be very difficult, and indeed in some cases it is. But some generic guidance is indeed possible on aspects of the modelling, in respect of the form of the model and in respect of meteorological effects. Some measurement models are straightforward and simple mathematical relationship, for instance, such as the ideal gas law, such as Ohm's law, such as Einstein's E=mc², a simple form of the measurement model. In a more complicated case, it might be very sophisticated in the form of, say, a partial differential equation, and therefore require numerical methods for its evaluation. JCGEM 103, the document we're developing, gives guidance, and this guidance is helped by including many examples, some simple, some more complicated. Further, more complicated examples are going to be given in a forthcoming document, and I'll say a little bit about that later. To emphasize what I said yesterday, the original GUM was published in 1993. It's now labeled JCGEM 100, and its first two supplements were 101 and 102. 101 concerned with Monte Carlo methods for a single measurand, a single output quantity, 102 for multiple measurands, and also a generalization of the law of propagation of uncertainty for multiple measurands, for implicit models, and for models involving complex quantities. JCGEM 101 includes a Monte Carlo method for propagating distributions, yielding for a scalar measurand, and we compute the value and standard uncertainty from the PDF or the histogram so produced. And we also provide a coverage interval or confidence interval for the measurand. JCGEM 102 extends those principles to any number of output quantities. LPU is generalized, as I say, to the multivariate case. An MC calculator of vector measurand and the covariance matrix is produced. And importantly, we don't have a coverage interval for the measurand anymore. Because the measurand is multivariate, we have a coverage region. And we indicate in 102 how that coverage region can be produced. Indeed, the coverage region of smallest volume is produced in 102. And I mentioned some other documents which are forthcoming. The main part of this talk is concerned with JCGEM 103 and what it provides. As I say, JCGEM Working Group 1 on the GUM hopes to publish this guide this year or next year. It's a new part in the JCGEM series, Guide to the Expression of Uncertainty in Measurement. That is the title of the current GUM. That title is being used as an umbrella title for the whole suite of documents that the JCGEM is producing. Why should we develop JCGEM 103? As I said, to propagate uncertainties, we need a measurement model. We need a relationship between the quantities we know something about and the quantities we want to learn something about, the input quantities and the output quantities respectively. We have the concept of a basic model, which depends on the measurement principle like Ohm's law, physical law, And we have variants of that model which have various degrees of sophistication. It depends on what uncertainty we need in our application. We call this a target uncertainty. The measurement model has to be developed to the extent that it can meet the target uncertainty. And we have the concept of an extended model. It's not a physical model, whether basic or sophisticated. It is a physical model extended to take account of the fact that the model involves measurement. And no measurement is perfect. We might have to introduce correction factors for the fact that we are not measuring temperature at the nominal value. Our actual temperature, actual ambient temperature, is different from that set in standard, say, and we have to make an appropriate correction. And JCGM 103 is including a classification of models really to facilitate their use on a computer. The first step in developing a model is to define the measurand. This, you might think, is obvious, but we have to be very careful in defining or specifying the measurand. The measurand, according to the VIM, the International Vocabulary on Metrology, is the quantity intended to be measured. Note the wording, intended to be measured. The purpose of measurement, you have to consider what is the purpose of our measurement. It gives us the choice of the measurand. And we need careful consideration. A simple example. Suppose we're given a sample of material. The material might be a hard material, it might be hard steel, it might be concrete, it might be a softer material like a plastic or a biological specimen. We want the hardness of that material. What does the hardness of that sample mean? Is it the hardness of the material overall, whatever that means? Is it the hardness at a specific point in the material? Is it the hardness averaged over the surface of the material? And the way in which we want to define our hardness helps to define the measurand. If we have a homogeneous material, it doesn't matter where we assess the hardness. If our material is inhomogeneous, it matters. And the various regulations, legislations or contracts, some embodied in standard, which can inform how to stipulate our measurand. I have a simple example here. The diameter of an engineering component. Suppose we have a diameter of component of nominal cylindrical form obtained from points measured on a profile of a right section of the component. So the left-hand diagram indicates a series of points marked by crosses, and the task is to compute the smallest circle which contains those points. That's the minimum circumscribed circle, MCC. Another calculation might involve the maximum inscribed circle. That's the largest circle which we can place within the set of points. And which circle we choose, in other words, which measurand we choose, depends on the function of the part, whether it's going to act like a piston or act like a cylinder, for instance. If you notice, these data points exhibit some lobing, that they form a shape exaggerated rather like a rounded triangle rather than a circle. That's because the machining process often introduces such an effect. It's highly exaggerated, of course, in this diagram, but it has to be considered as an influence quantity. We're talking about modeling the measurement principle. As I said, it's often based on a scientific law. Perhaps it's based on a combination of laws. The input quantities are the quantities appearing in those laws underlying the measurement, and they follow from the measurement principle. The output quantities constitute the measurand. The measurement model, as I say, is a relationship between the input quantities and the output quantities, and the diagram below illustrates this simple concept. It's simple in concept, but often difficult in practice. Form of the model. The measurement model can be classified in various ways. depending on how it was formed. Often we have a theoretical or scientific model. We have a law, such as Ohm's law, such as E equals mc squared. There are many other laws occurring throughout physics. They form a theoretical basis or a scientific basis of the model. Sometimes we don't have a law in place. The measurement model has to be based on an empirical relationship, such as a polynomial, for instance. Many measurement models are both theoretical and empirical. In other words, we have a theoretical law as the basis of what we want to do, but the theoretical basis is not sufficient. We must augment that basis by some empirical terms, and we call this a hybrid model. Another criterion of classification, as I said before, we might have a single output quantity or a multiple or vector output quantity. There's a further distinguishing criteria in building a measurement model. We can have an explicit relationship. I'm going to give an instance of an explicit relationship. Y is a function of x. An implicit relationship where we can't write down directly y as a function of x, but we're in a position to calculate y given the values of x. The measurement model, as I say, can contain quantities that are real or complex. The measurement model might constitute one stage of several stages. Take calibration, for instance. Calibration, we want to calibrate an instrument, and then we want to use the calibrated instrument. So there are two stages in calibration. And so we talk about this scenario as a multi-stage measurement model. And we also contemplate statistical models. Statistical models we also regard as categories of measurement model. A little bit about that later. Choices in selecting or developing a model. Obviously, we want a model that is adequate for the case in hand. We want a model that is fit for purpose. For all these classifications of model, theoretical, empirical, or hybrid, we should account for the target uncertainty to ensure our model is fit for purpose. Another factor to take into account, what resources do we have available to build our measurement model? Building a sophisticated measurement model might necessitate experienced personnel. It might necessitate sophisticated software, etc. So there are some conditions we must attach to building a measurement model. For empirical models, it might be the choice of a straight line or a polynomial of high degree, or possibly a Fourier series, or some other representation by an empirical model. Some choices can be much better than others, of course, including an effect on the numerical behavior when the model is implemented on a computer, and I'll give an example of that later. The choice of model introduces another uncertainty. It's not a measurement uncertainty, but it's a model uncertainty. Suppose we have some phenomenon that we try to describe by a polynomial. The choice of degree influences how well we can represent that phenomenon. And so we have the concept of model uncertainty. Model uncertainty in the choice of degree in that instance. And that's another very important consideration. And our document JCGM 103 considers model uncertainty. And as I say, we have to consider the measurement. You have to consider the metrology involved. The need for correction terms, I mentioned temperature as an example, measuring at slightly the wrong temperature. And we have to incorporate correction terms in our model to allow for those effects. The correction terms can be additive or multiplicative. A simple example of a theoretical model, the mass of a spherical weight. You can imagine a sphere machined from some material. We have a simple formula relating the diameter of the sphere and the density of the material to the mass of the sphere. But this model is idealized. It's a physical model which holds in perfect conditions. The geometry of the sphere must be perfect, and the sphere must be perfectly homogeneous. The model describes a transformation, if you like. It describes a transformation from a diameter and density to mass. But there are meteorological effects. We might have imperfect geometry. We have to account for that imperfect geometry. We might have inhomogeneity. We should account for that. And we can account for that effect using correction factors in our model as indicated there. Often these correction factors are as important as any uncertainty on the diameter and the density. I mentioned implicit measurement models where we're unable to write down the measurand, explicitly as a function of the input quantity. This is one project that I worked upon, the shell thickness of microscopic spherical particles. In this case, we want to calculate an equivalent planar thickness T and multiply it by a geometrical correction term. The details don't matter too much, but the important point is the equation in the middle of the screen there is an implicit model involving T, the measurand, and two input quantities A and B. It's impossible to express T explicitly in terms of A and B. But given any values for A and B, we can solve that equation for the corresponding value of T. So it's an implicit model, and it has to be handled slightly differently from the handling of an explicit model. And JCGEM 102, the document I mentioned that's concerned with multivariate quantities in implicit models as well, gives tools for handling such an equation. And we can indeed propagate standard uncertainties through that model. Given the standard uncertainty associated with A, the standard uncertainty associated with B, we can indeed propagate through that model to determine the standard uncertainty associated with T. That was an example of an implicit model where we knew the science. We knew the actual equation based on theoretical considerations. This is an example of an implicit empirical measurement model where we don't know the physics, and we use empirical representations of the model. This is a model of a platinum resistance thermometer giving resistance as a function of Celsius temperature T over an interval, quite a large interval, minus 200 degrees Celsius to 800 degrees Celsius. An empirical formula is known as the Callendar-Van Dusen equation given there. So you see this empirical formula has a different form over two subintervals of the total interval of length 1000 degrees Celsius. The quantities on the right, R0, A, B, and C, are determined by calibration and hence have uncertainties. Indeed, they have an associated covariance matrix. We use the equation inversely because we want to compute the temperature T having measured the resistance R. So again, we want to use the expression inversely. And it requires the use of an appropriate algorithm, of course. We have the concept of a hybrid measurement model. And I give an example. Again, I worked on this project, the spectral irradiance of a lamp. The light emitted from such a lamp approximates that of a black body. It might approximate that of a black body well, it might approximate it rather poorly. The spectral irradiance of a black body source is modelled using the Planck function given in the middle of the screen there, where lambda is wavelength, T is the black body temperature, and C1 and C2 are known constants related in fact to the fundamental constants of physics. Lamps are not ideal black body sources, but the irradiance in all cases varies smoothly with wavelength lambda. And so we model the spectral irradiance of such a lamp by a product of a Planck function and a correct function. The correction function we use is a polynomial, and we found it works extremely well in practice. Here we have a set of data, measured values of the spectral irradiance of a certain lamp, denoted by crosses in the left-hand picture. If we fit a Planck model to that data, you can see it fits, well, rather poorly. There are regions near the peak, the regions near the right-hand tail, where the fit doesn't really represent the data too well. But the hybrid model, the product of the Planck function and a polynomial in the right-hand picture, we use degree 10, approximates it rather well. That was the best choice of degree. We use an information criterion to choose the degree. We can choose a lower degree if we wish, but we won't have such a good approximation. For instance, degree 5 gives a standard uncertainty 4 times as large as that of degree 10. Degree 2 gives a standard uncertainty 12 times as large. So if we wish, we can match the degree to the target uncertainty, the need for certain precision in certain applications. Single or multiple measurands. Many examples in the GUM and in other guides, European Accreditation Document 402, have single measurands. There are very few published, respected international documents that give examples for multiple measurands. We want to redress the balance by giving a number of examples in that respect. A very simple example is an image or a textured surface, in this case measured over a mesh. And often we filter the measured values, perhaps using a Gaussian filter, using a triangular filter, to remove some of the noise in the data. But that computation, the actual filtering operation, induces correlation because we're combining adjacent values, linear combination of adjacent values, and so the resulting filtered values have correlations induced by that filtering process. And we must take account of that correlation if we're going to work with the filtered values rather than the original values. Often you have software provided by various companies, or you read various papers that don't take account of that filtering, in which case invalid conclusions can be drawn regarding the corresponding uncertainties. A simple example which already occurs in the GUM. The GUM, although it doesn't treat multiple measurands, it gives an example of a multiple measurand. It's a very simple example. Resistance R and reactance X are given by measuring the amplitude V of an alternating potential difference applied to a circuit element, where I is the amplitude of the alternating current passed through it with phase angle phi. The GUM quotes the bivariate measurement model in the middle of the screen. R and X are the output quantities, V, I, and phi are the input quantities. Given estimates of the input quantities, V, I, and phi, we want to compute estimates of the output quantities, R and X. Because R and X depend upon the same input quantities, their values we obtain by using those formula are correlated. And if we're going to use the values of R and X in a further calculation, we must take account of the correlation, otherwise an invalid uncertainty statement can arise. As I said at the beginning, it's necessary to extend the basic model, perhaps to make it more sophisticated theoretically and to account for the metrology. Physical laws describing the measurement principle hold in ideal conditions. And laws may have variance. We might have a basic model, we might have a sophisticated model. In the real world, and as metrologists we're concerned with the real world, we must take account of ambient conditions and other non-ideal situations. These situations introduce systematic effects that need to be taken into account. So JCGEM 103 includes generic material for correcting for those effects, sometimes shared systematic effects if we have multiple measurands, an effect influences each input quantity. And it also covers the modelling of drift, aging and other time-dependent effects, because that's real metrology. Instruments drift, instruments have to be recalibrated, instruments age because they wear, and so on. A more sophisticated measurement model is illustrated by a correction due to air buoyancy in a mass comparison. Air buoyancy exerts an upward force on an object. If we weigh an object in a vacuum, obviously we don't have to take account of air buoyancy. If we measure in air, we have to take air buoyancy into account if a target uncertainty warrants that consideration. We can do, and the consequence is we have a smaller associated uncertainty relating to the result than we would have by not taking account of buoyancy. An example from chemistry of a more sophisticated theoretical model involving corrections is cadmium release from ceramic wear. All ceramic objects, including domestic objects, tend to release cadmium at a certain rate. A measurement model for mass R of cadmium leached per unit area is given by the expression in the middle of the screen, where the input quantities are listed there, C0, VL, AV, and D, and the output quantity is the mass R in which we're interested. It's a very simple model. It's a multiplicative model with one term in the denominator. We want, of course, to compute an estimate of the mass R given estimates of the input quantities on the right-hand side. That equation is fine, but it doesn't take account of what is happening in our measurement situation. But that measurement can be modeled by taking account of the metrology using correction factors. We have the same model illustrated there, but the correction factors are indicated in red. F acid, F time, and F temp are multiplicative correction factors modeling the effect of acid concentration, the duration of the digestion, and the temperature. Our best estimates, all correction factors are equal to 1, which means the modified model gives exactly the same value for R as the unmodified model. But if we're considering uncertainties, which we are, the modified model gives a different associated uncertainty. It gives a larger uncertainty because we take account of uncertainties relating to F acid, F time, and F temp. So that's a very simple example of how to include correction factors in a measurement model obtained from scientific considerations. Time-dependent effects are becoming more and more important in metrology because of the need to increase the accuracy, the need to have smaller uncertainties. We give a simple example in 103, which might be the example I'm giving now. It might be replaced by another example, but at least this example illustrates what I want to say. We have a weight which is measured periodically over a long period of time. The weight has nominal mass 1 milligram, and has been calibrated 100 times between 1992 and 2011. This mass is used as a reference mass when we want to compare a nominal 1 milligram mass with the reference mass. Masses change over time due to surface contamination and periodic cleaning of the mass. This effect seems to be linear in time. And you see the masses indicated in the diagram below. the masses have uncertainty bars on their values as expected. And we model this effect over time by, in this case, a straight line, and the straight line satisfies reasonable criteria. We don't need a higher degree polynomial. The model is used to provide a predicted value and an uncertainty associated uncertainty under the assumption that the linear trend continues. We could argue that that behavior in the diagram has some periodicity associated with it, and a very sophisticated model might try to take account of that effect. Another influence is repeated observations. When we take repeated observations, we want repeated observations when we are averaging them in an attempt to reduce the associated uncertainty. If they're genuine repeated observations under constant measurement conditions, we expect the average of those observations to have a smaller uncertainty than an individual observation, which is indeed true. But in situations where the measurement conditions aren't constant, that uncertainty associated with the mean is larger than it would be assuming independence of the observations. If we don't account for that effect, we can provide misleadingly small uncertainties. The GUM, JCGM 100, the respected document GUM, gives guidance for independent observations, and they refer the user of the guide elsewhere otherwise. JCGM 103 is including an example or two to illustrate such effect. The diagram below indicates some 100, I think, points connected by straight lines just for visualization purposes of the temperature of a thermal bath. The thermal bath is controlled in temperature and to lie in a certain interval. The behavior is clearly not random. It has some randomness associated with it, but it's not purely random. And so the observations are not independent. Halfway through the chart there, you can see the observations have a tendency to rise with time. We want to take account of the dependencies, and so we fit an appropriate model. It's called an ARIMA model for the statisticians among you, which account for those effects. I'm not going to go into the details, but if we fit an appropriate model which takes account of the actual behavior of the observations rather than assuming they're independent, we get essentially the same, in fact exactly the same mean value, but we get a standard deviation associated with mean which is 3 times that which we would have obtained assuming they're independent under that naive assumption. And so it makes a difference. We must ensure our model is adequate. We must ensure we make a sensible choice of model. And the message is here, do not extrapolate with empirical models. Never extrapolate with empirical models. But if you have an analytical model, a model based on a scientific law, a scientific principle, extrapolation is less dangerous. This example comes from isotope dilution, and this area is interesting because it differs from many methods of analytical chemistry because we have a physical calibration function. We have the calibration function in the middle of the screen, which is bilinear. It's linear in the input quantity Q, and the A0, A1, and A2 are associated calibration parameters provided by regression from given data. And we can extrapolate with this this good model, this analytical model. We can extrapolate to provide values beyond the span of the measured data. And if we were to measure that value beyond the span of the measured data, we would normally find this extrapolated model works well. And that diagram illustrates it. And you can see on the screen Pardee 1,1. Pardee 1,1 is the mathematical statement of what this bilinear model represents. But most users we found in analytical chemistry like to work, well, naturally, with simpler models. They don't like nonlinear regression. And so they attempt a linear polynomial, they attempt a quadratic polynomial, they might attempt a cubic polynomial. And so you see, beyond the span of the data, although these models work rather well over the span of the data, the 5 points indicated in the diagram, they work very badly extrapolated very far from the span of the data, whereas the analytical model works surprisingly, well, perhaps not surprisingly, it works well. And so using an empirical model is really unacceptable and can make a tremendous difference in practice. There are numerical aspects which must be taken into account. I'm a numerical analyst. I did my PhD in numerical analysis, so this is one of my favorite subjects. Looking at the effect of the computer, the effect of the finite precision of the computer on calculations. The diagram here, the erratic black line represents a polynomial degree 6 evaluated at 101 points uniformly spaced over the interval connected by straight lines. That's not a polynomial. That's not a polynomial. A polynomial doesn't wobble that much, certainly at degree 6. The true polynomial evaluated, if you use much greater precision, will be the red line. What is happening here? If we wanted to evaluate P at its minimum, the red curve has a single minimum, but the black curve has many minima. And so we have a problem. Behavior is highly erratic, nothing like the smooth behavior of a polynomial. Can anybody suggest what's going on? It is the effect of floating point precision. If we carried out the calculation using not 16 decimal digits, which a typical computer has, if we use 32 digits, would reproduce the black curve to visual accuracy. But often we use 16 digits, and we think 16 digits is easily enough. What's going on? This is what's going on. We computed the polynomial from the expression in the fifth bullet, px equals 1 minus 6x, etc. That looks a respectable polynomial. It is a respectable polynomial. But we're evaluating it near 1. If you remember, the interval was between 0.99 and 1.01. If we evaluate that near 1, we have immense subtractive calculation. Respective terms in that expression cancel, and the values of individual terms are much, much greater than the final value of the polynomial. The final value of the polynomial is the order of 10 to the minus 13 at x equals 0.99. But some of the individual terms have magnitudes of order unity, order 10. And so we must have extreme cancellation on that. In fact, that polynomial p of x is in fact the polynomial given in the last bullet, 1 minus x to the 6th. By multiplying that out and using that expanded form of the polynomial, we suffer from this subtractive cancellation. So we must pay attention to the actual form of the function we're working with. It's surprising, it surprises many people, but it's a fact of life. Why should we expand it anyway? Why not work with the original form? The reason we might expand it is that we're using standard polynomial software, which expects the coefficients of that polynomial to be provided to it. And so that's an awful warning. Apparently a very innocent problem can produce wrong results, and you might be misled as a consequence. I conclude with some comments and some take-home messages, if you like. I've tried to outline some key aspects of the document JCGEM 103 we're producing. It's soon to be circulated to the National Metrology Institutes, the JCGEM member organizations listed there, and they and you will have an opportunity to comment and request, if you think it's appropriate, additional material. Many more examples are going to be covered in the related document JCGEM 110. The take-home messages are as follows. We start with a model based on a measurement principle. We extend the model taking account of metrological effects, correction factors, etc. We ensure the model is fit for purpose, accounting for the target uncertainty. We should check whether repeated observations are independent. Plots are very good in this respect. We ensure we do not extrapolate with an empirical model, and we must avoid numerical traps, such as the one I just indicated, subtractive cancellation. Thank you very much.
Tenemos tiempo para preguntas.
Ahí marcó un factor de tiempo, un factor de concentración y un factor de, no sé si fue presión o alguna otra variable. Temperatura, ajá, es temperatura, concentración y otro factor, y tiempo. En ese caso, cuando se tienen datos experimentales y todo, no sería conveniente o no se usa también, en lugar de meter factores de corrección, meter eso dentro del mismo modelo y el modelo acotarlo a un rango del experimento. Por ejemplo, este modelo es válido de tal condición a tal condición y se establece, ¿no? Como una ecuación de estado o como un modelo matemático acotado, ¿no? Es mi pregunta, que si en lugar de los factores, como él menciona, que se utiliza mucho el modelo matemático, los polinomios de sexto grado o menos grado, si se puede en un momento dado incluir esos factores dentro del modelo matemático.
Okay. Did you get that?
No.
Okay, he's talking about the correction. Okay, just to make sure. He's talking about the correction factors. So he's asking if it wouldn't be more convenient to incorporate those correction factors within the model, not as multiplying factors for the output quantity, but within the model. Maybe specifying a range of the input variables and say, okay, this model is valid within this range, and it might be a different model for another range. So that's a question.
Your suggestion is a good one, and that could indeed be done. In our work, we choose to separate the effects. We start with the measurement principle, we develop a model, a scientific model based on that principle, and then we consider the metrology as additional effects. We could combine, of course we could, and consider individual ranges in which the model is combined. We think naturally along the lines we've proceeded, but we could have indeed gone along your lines.
Morris, ¿por qué se tardó tanto o se está tardando tanto en salir la guía de mínimos cuadrados?
That's a challenging question. As you said yesterday, least squares is important, and we recognize that. The JCGEM committee on which I work has about 12 or 14 members. As with many committees, the experts on that committee are very, very busy people. And so a lot of those experts are unable to devote sufficient time. They give good opinions at the meetings, of course, but between meetings are unable to devote too much time. On the other hand, we have 3 or 4 experts on the committee who can devote some time. I can devote some time because my company, the National Physical Laboratory, has a program of work in which I have a dedicated number of months per year which I can devote to the JCGEM documents. That's the sheer reason why we aren't able to develop we'd love to develop all these documents simultaneously, but in practice that's impossible. And so it's good that we've got this European grant for the examples document, which will feed in to many of the documents, including the least squares document. And I could mention your comments to the JCMJ committee. We meet next month, and they will take account of the fact you've expressed a need for the least squares document. I hope they do anyway.
Para cuando en el modelo matemático uno de los valores de las magnitudes tuviera uno que obtenerlo a partir de una interpolación, por ejemplo, no sé si recuerde la ecuación de Arrhenius, ese valor de la magnitud obtenida por interpolación, ¿se le asocia una incertidumbre? ¿O cómo podría yo calcularle esa incertidumbre? ¿Cuál de los documentos que menciona me podría ayudar a calcular una incertidumbre? ¿O considera usted que no tiene incertidumbre?
And so when we interpolate, we need an interpolating function. For instance, if we use a straight line interpolation between 2 points, and the interpolated value has an uncertainty, and it depends on the uncertainties associated with the 2 individual points from which we're interpolating. If we used a quadratic for the interpolation function, we'd need 3 points, and we'll get a different value, perhaps not very different value, but we'll get an according uncertainty. So in the first instance, we must choose an interpolating function, and depending what interpolating function we're choosing, we have to propagate the uncertainties from the data we're interpolating through to the interpolated value. Is that sufficient?
Muy bien. Creo que tenemos tiempo para una pregunta más.
This is associated with the last question. When you have some discrete points, but you want to calculate the derivative, what are the recommendations for calculating the uncertainties of the derivative?
If I understand you correctly, we have a set of points, a set of discrete values, and you want to provide a derivative at one or other of those points.
Or intermediate points, I mean.
Intermediate points.
And you have uncertainties or errors at the points.
Of course. Again, you have to use an interpolating function or perhaps some regression function that you fit to the points by least squares, for instance. Say we're doing the latter. And so we have several points with uncertainties associated with those, and we fit perhaps a quadratic polynomial, perhaps, and we test whether that quadratic polynomial is suitable for that data. If according to our statistical test it is suitable, we can take the derivative at any point within the span of the data, and we can propagate uncertainties from the original data points through the calculation, whatever the calculation is, through the calculation to obtain the uncertainty on not the interpolated value, but on the derivative at the interpolated value. Any calculation we can propagate uncertainties through. Any calculation. And you say, if you use the law of propagation of uncertainty in the GUM, you require derivatives, sensitivity coefficients to propagate uncertainties. If you have a calculation in the form of an algorithm, you can indeed form the derivative numerically. And there is a way known as the complex step method which enables the calculation of those sensitivity coefficients to the accuracy of the computer. That's another lecture.
Thank you very much.
Bueno, entonces los invito a que agradezcamos al profesor Cox por sus 2 charlas de esta. Y le hacemos entrega de un pequeño reconocimiento.